Okay, as we move from rates and ratios, we're going to move into something called the constant of proportionality. And the constant of proportionality is the constant unit rate associated with different pairs of measurements in a proportional relationship, meaning you are doing something at a constant rate. If I'm going 5 miles an hour, I went 5 miles, then 10 miles, then 15 miles, then 20 miles. I'm constantly going a certain amount of miles. And we can use the word constant proportionality. It's another term for unit rate when one object's being repeated constantly. Now, we can take this information and go to a graph on a coordinate plane. You will be taking this information to a graph when you get into what's called slope. But for right now, we can take this information and graph the results in a coordinate plane. And here's the important part. Since it is a proportional relationship, it should be a straight line that goes through the origin. And now, because you're dealing with a lot of times real life problems, we're only going to be dealing with the first quadrant, because we want it to all be positive. You don't get negative distances or negative speed or negative amounts when dealing with real world problems. Now let's take a look at constant of proportionality in a word problem setting. Grandma Betty rode her bike to the tobacco trail. It took her 4 hours to ride 12 miles. Assume she rode at a constant rate of speed during the exercise. So when we look at the table, notice that I put time and miles. So it took her 4 hours to ride 12 miles. Now, let's think of it this way. For time, we're going to count backwards in hour-long increments. 3 hours, 2 hours, 1 hour, and then 0 hours. Now, if she's been riding 0 hours, logically it makes sense to say she's gone 0 miles. To figure out the unit rate, to say she's been riding for 1 hour. To figure this out, we can divide 12 by 4. And that tells us that each hour she's ridden 3 miles per hour. So in 1 hour she rode 3 miles. That means in 2 hours she rode 6 miles. And in 3 hours she rode 9 miles. So see how each one's going at a constant speed? For each hour she rode 3 miles. Now we want to put this on the graph. So what we're going to do is we're going to use our table to determine where to put the dots on the graph. Remembering that if this is going to be a constant rate of proportionality, it should be a proportional relationship, we should have something that looks like a straight line and it should go through the origin, meaning 0, 0. So in order for me to graph it, we're going to have to zoom in to make it look the way it should. Now the first one says after 4 hours she rode 12 miles. So using our graph, we can put a dot where 4 hours, notice that time's on the x-axis and miles is on the y, where 12 and 4 intersect, we can place a dot. And then it says for 3 hours, she rode 9 miles. And then it says for 2 hours, she rode 6 miles. So for 3 hours, she rode 9 miles. I put a dot where it said 3 hours and it meant with 9 miles. For 2 hours, I put a dot where the line for time was 2 and the miles was at 6. 1 hour represents 3 miles. So we put a dot at 1 and 3 to represent that in 1 hour she rode 3 miles. And then starting at the origin, 0, 0, we have to put a dot to represent that if she's not been riding at all, if she's been riding 0 hours, she hasn't gone anywhere. She hasn't gone riding at all. So now I'm just going to fill in my dots to make them look a little bit better for when we zoom out. And there is our graph to match our chart. And it says that it's supposed to make a straight line. So let's see if we can, in fact, make a straight line. Yours are going to be a lot straighter than mine, so please use a straight edge and draw a line. And notice that, yes, it does make a straight line. Yours is going to look straighter than mine because yours is using a straight edge and I had to freehand it. Now, we're going to answer some questions regarding our graph. It says you move up blank units for each 1 unit move you move right. So every time I move to the right, when I go from 0 to 1, I went up 3. When I went from 1 to 2, I went to the right 1, but I still went up 3. It says when you moved up 2 times each 2 units. So I'm still moving 3 units to the right, but when I went over to 2 hours, I had to go up 3 times. I had to do that twice. When it says when you do 3 hours, that means you're going up 3 times. You're going up 3 spaces and you're doing that 3 times. And then same for 4. It says that if you're going to go to 4 hours, it means I went up 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I moved up 1, 2, 3. I did that 4 times. Now, starting at 0, 0, to get to a point x, y on the graph, you will go up x times 3 units. Makes sense, right? 3 was this number. I'll give you a hint. 3 is the constant because you're going up 3 units every time. We can put this into an equation to say y equals x times 3, or a little simpler put, y equals 3x for that. But that's what our equation would be, y equals 3x. So now, let's take a look at these questions we have down here. What is the ordered pair when x is 1? When x was 1, you went over 1, you went up what number? You went up to 3. What does it stand for? Well, it stands for 3 miles for 1 hour, because it meant I went over 1 hour and I went up to 3 miles. The constant of proportionality in this case is going to be 3, because 3 is this number that keeps happening. And what is the constant of proportionality equal to? It is equal to the unit rate. Constant proportionality is always equal to the unit rate. Now, it says Grandma Betty doesn't always ride 12 miles, but she always goes at the same pace. And we want to use our equation, this y equals 3x, or rather, miles equals 3 times time, to help us out. So it says use that equation to help us with the information on different sessions. So it says she rode for 6 hours and 30 minutes. Now, the first thing that we have to know is that 6 hours and 30 minutes is 6.5 hours. We can't have any mixed units within the problem. So what we would do is we would put in, we know that 30 minutes is half of an hour, so 6 hours and 30 minutes is 6.5 hours. We can then fill that information into our equation. We have that miles equals 3 times our time. So we would have miles equals 3 times our time of 6.5. And that means that she traveled 19.5 miles. Now, what if they gave us the other unit and they said she rode her bike for 15.75 miles? In the equation, miles equals 3 times time. So they gave us the equation, they gave us that it was 15.75 miles, and we found that by doing 3 times the time. It said, how long did it take her? Well, we know to solve this equation, we have to do the inverse of multiplication, meaning we are going to divide. So we take 15.75 we divide it by 3, and that's going to tell us the time. So this tells us that she rode for 5.25 hours. Now, that's the first part of this question. The second part says, can you convert this to hours and minutes? Well, the hours are going to be the whole numbers, so we know that it's going to be 5 hours. To figure out the minutes, a lot of times students' inklings or like intuition tells them, hey, it's 25 minutes. The problem with this is that 0.25 is not 25 minutes. In an hour, there's 60 minutes. So we will say that, so we can say that time is based off of kind of a base unit of 60. Everything is out of 60. 60 seconds, 60 minutes, 60 hours. 0.25 decimals are based on out of 10, because it goes tenths, hundredths, which is 10 times 10, thousandths, which is 10 times 10 times 10. So we say that that decimals are a base 10. Because you have these different amounts to measure, it's not as simple as saying it's 25 minutes. What we have to do is we have got to multiply our decimal, which is 0.25, times 60, because there's 60 minutes in an hour. And if we take 0.25 times 60, we get 15. This means that it will take her 5 hours and 15 minutes. Anytime you're dealing with time and you're asked to convert from a decimal to hours or minutes, it's all based off of multiplying or dividing by 60 anytime you're dealing with time.